Hey guys, in this video we will be going over sets and compound inequalities. So let's talk about what is a compound inequality. A compound inequality is just two inequalities joined by the words and or. So for example, x plus 3 less than 8 and x is greater than 2 is a compound inequality joined by the word and. And then another example is x is greater than or equal to 5, or negative x plus 10 is less than 5, which is a compound inequality joined by the word or. We'll start talking about the and conjunction. This is also known as an intersection and denoted by this symbol. All right, let's go over what the intersection of two sets looks like. So the intersection of two sets, say A and B, is the set of all elements common to both sets. We can use a Venn diagram as a visual representation. The intersection of A and B would be the region in between, since this region is common to both. All right, so let's apply this to an example. We wish to find the intersection of two sets. So let set A include elements 2, 4, 6, 8, and let set B include elements 3, 4, 5, 6. So A intersect B, which is also the symbol for and, will be the elements that are common to both sets. So 4 is common to both, and 6 is common to both. Therefore, A intersect B is just 4 and 6. Okay, now let's apply this to compound inequalities containing the word and. So a value is a solution of a compound inequality formed by the word and if it is a solution to both inequalities. Okay, so let's consider the following compound inequality. The solution set of this will contain all values of x that make x is less than or equal to 5 a true statement, and x is greater than or equal to 3 a true statement. So we'll start with graphing the solutions to the individual inequalities. So to graph x is less than or equal to 5, we place a closed circle at 5 and shade everything less than 5. And to graph x is greater than or equal to 3, we place a closed circle at 3 and shade everything greater than 3. So looking at the graphs, what solutions do they have in common? It looks like they have 4 in common, 5 in common, 3 in common, and just everything in between. Therefore, they have common solutions in this region. So the graph of the compound inequality will be the region between 3 and 5, including 3 and 5, with closed circles. So to represent this in interval notation, our minimum is 3 with a bracket since there's a closed circle, and the maximum is 5 with a bracket since there's also a closed circle. And just as a note, we can represent this inequality in the following manner, where x is between 3 and 5. And we'll explain that in a little bit. So some compound inequalities containing the word and can be written in a more compact form. If we have the following compound inequality, x is greater than or equal to 2, and x is less than or equal to 6. The compact form of this is writing x in the middle and having it be greater than or equal to 2 and less than or equal to 6. For the graph of this, we'll have a closed circle at 2 and 6 and shade the region in between. And expressed in interval notation, we have the minimum at 2 with a bracket and the maximum at 6 with a bracket. Okay, so let's try an example. We want to solve the following compound inequality. First, we need to solve the inequalities separately. We're going to need to isolate the variable x, so add 7 to both sides of the inequality. This cancels out the minus 7 plus 7 on the left, and we have x is less than 2 plus 7, which is 9. And now the inequality is solved for x. For the second inequality, we're going to minus 1 to both sides. This cancels out the plus 1 minus 1 on the left, and we have 2x is less than 9 minus 1, which is 8. Then we divide both sides of the inequality by 2, and this simplifies to x is less than 8 divided by 2, which is 4. The compound inequality now becomes x is less than 9 and x is less than 4. So to figure out the solution to the compound inequality, let's graph the inequalities separately. For x is less than 9, we place an open circle at 9 and shade everything less than 9. For x is less than 4, we place an open circle at 4 and shade everything less than 4. Okay, so now to graph the solution to the compound inequality, we need to find their intersection. So what do they have in common? It looks like everything to the left of 4 is common to both inequalities in this region. Therefore, the graph of the compound inequality will include an open circle at 4, since we have an open circle here, and shade everything to the left. This will be our solution in set notation, which is the same as the set of all values of x such that x is less than 4. The solution in interval notation will be a minimum at negative infinity with the parentheses and a maximum at 4 with the parentheses. Okay, so let's try another example of a compound inequality joined by the word and. Again, we solve the individual inequalities separately. For the first inequality, we divide both sides by 2, and this simplifies to x is greater than or equal to 0 divided by 2, which is 0. For the second inequality, we add 1 to both sides, and this simplifies to 4x is less than or equal to negative 9 plus 1, which is negative 8. Now we divide both sides by 4, which simplifies to x is less than or equal to negative 8 divided by 4, which is negative 2. Okay, so our compound inequality simplifies to x is greater than or equal to 0 and x is less than or equal to negative 2. So let's first graph the individual inequalities in order to visually see where the common solutions are. Okay, so what do these inequalities have in common? It looks like there is no overlap, which means they do not have any common solutions. Therefore, there is no solution to this compound inequality. Okay, so to solve a compound inequality like 2 is less than 4 minus x less than 7, we need to get x alone in the middle. So we use our properties of inequalities on all 3 sides. So for example 4, we need to solve the inequality for x, meaning we need to isolate x and get it alone in the middle. So we subtract 4 from all 3 sides and simplify. Now the last step will be to get rid of the negative in front of the x, which is really a negative 1. Therefore, we divide all 3 sides by negative 1. Now remember, we're dividing by a negative number, so we will need to reverse the inequality symbol. So we have 2 is greater than x, and x is greater than negative 3, which is equivalent to negative 3 is less than x, and x is less than 2. The solution written in set notation is the set of all values of x such that x is between negative 3 and 2. We can graph this with open circles at negative 3 and 2, and we shade everything in between. And then the solution in interval notation is a minimum at negative 3 with the parentheses, and a maximum at 2 with the parentheses. Okay, so let's try another example. For this, first we can multiply each side by the LCD, which is 3, to clear the fraction. So we need to multiply all 3 sides by 3 and simplify. Now, to isolate our x, we will subtract 15 from all 3 sides. And finally, we divide all 3 sides by 2. Negative 9 over 2 is already simplified, so we can just rewrite this as is. Now x is by itself in the middle. And now to express our solution in set notation, and then on a graph, so x is between negative 9 and negative 9 over 2, which is the same as negative 4.5. So we place a closed circle at negative 9 and an open circle at negative 9 over 2, and then shade everything in between. Then the solution in interval notation, we have a minimum at negative 9 with a bracket, and a maximum at negative 9 over 2 with a parentheses. Okay, so now let's talk about the OR conjunction. This is also known as a union and denoted by this symbol. So let's go over what the union of 2 sets looks like. So the union of 2 sets, say A and B, is the set of elements that belong to either of the sets. Again, we can visually represent this using a Venn diagram. So the union of the 2 sets will be the regions that belong to either set. So everything in set A and everything in set B. So just make sure you know the difference between intersection versus union. Alright, so let's try an example. We want to find the union of the sets. So let set A include elements 2, 4, 6, 8, and let set B include elements 3, 4, 5, 6. The union of set A and B will be the elements that belong to either set A or set B. So we just grab the elements from each set. A union B will include 2, 3, 4, we can just list this once, and 5, 6, and 8. Essentially, we're just taking the elements in either set and putting them together. Alright, so let's now apply this to compound inequalities containing OR. A value is a solution of a compound inequality formed by the word OR if it is a solution of either inequality. So let's consider the compound inequality x is less than or equal to 1, or x is greater than or equal to 3. The solution set of this will contain all values of x that make x is less than or equal to 1 a true statement, or x is greater than or equal to 3 a true statement. First, we can graph the inequalities separately. Place a closed circle at 1 and shade everything less than 1. For the second graph, place a closed circle at 3 and shade everything greater than 3. Now the graph of the compound inequality will include solutions to the first inequality and the second inequality. So we can just place this on the same graph. Now, how do we write this solution in interval notation? We have to find the minimum and maximum for the region on the left side. Then for this break, we will use the union symbol, and then we write the minimum and maximum for the region on the right side. So our minimum for this side will be negative infinity and a maximum at 1. Negative infinity gets a parentheses and 1 gets a bracket. Then a union for the gap. And a minimum for the other side will be 3 with a bracket and the maximum at positive infinity with a parentheses. For the next example, we use the same procedures. First, we solve the inequalities separately. So to get rid of the minus 3, we add 3 to both sides and simplify. Next, to get rid of this 5, we divide both sides by 5 and simplify. And we are just left with x is less than or equal to 3. For the other inequality, to get rid of the plus 1, we subtract both sides by 1. Simplifying, we get x is greater than or equal to 5. So our compound inequality simplifies to x is less than or equal to 3, or x is greater than or equal to 5. Okay, so for the or compound inequalities, we can just take a shortcut and graph the solution on the same number line. So to graph this inequality, we place a closed circle at 3 and shade everything less than 3. And to graph the other inequality, we place a closed circle at 5 and shade everything to the right. Again, you could only do this shortcut for the or compound inequality. We can express our solution in set notation and then in interval notation. So we need to write the minimum and maximum for this region and this region, and include the union symbol for this break. The minimum for the shading on the left is -infinity, up to the maximum at 3 with a bracket. For the gap, we write the union symbol, and the other region has a minimum at 5 and a maximum at +infinity. All right, for our last example, we have the following compound inequality. So start by solving the inequality separately. For the first inequality, to get rid of the -5, we add 5 to both sides and simplify. Then we divide both sides of the inequality by -2. But remember, since we're dividing by a negative number, we have to reverse the inequality symbol. So we have x is greater than -1. For the other inequality, we divide 6 from both sides, simplify, and we get x is less than 0. So our compound inequality simplifies to x is greater than -1, or x is less than 0. So because this is an or compound inequality, we can use the shortcut again and graph the solution to the compound inequality on the same number line. Place an open circle at -1 and shade everything greater than -1. Then place an open circle at 0 and shade everything less than 0. So the two open circles actually get enclosed with the shading. Therefore, our graph just looks like this, where the entire number line is shaded. We can write the solution in set notation, where we have the set of all values of x such that x is greater than -1, or x is less than 0, which is really the same as all real numbers. And for interval notation, our minimum is at -infinity, with a maximum at +infinity.